Welcome to this action-packed dive into the world of data modeling. In the next few minutes, we are going to break down exactly what a data model is. And trust me, by the end of this video, you will be building some data models yourself. We'll start by crafting an entity relationship diagram, showing you how to create a data structure that makes sense for you. Then we'll take it up a notch, converting our ERD diagram into a third normal form. Finally, we'll transform that into a Star Schema. Ready to become a data modeling master? Let's get started. So what is data model? Data model is used for database design purpose. So whenever you are building a new database, you have to start from a scratch. Then you build a data model first to see how graphically your database will look like. The very first step of designing a data model is entity relationship diagram. An ERD, in short, gives you an overall impression of your databases in graphical format. It is used for converting diagrams into relational tables. Entity relationship diagram consists of two components: entity, which are like real-world objects, concepts, and are represented by a rectangular box in the diagram. Some examples of entities are students, courses, faculty in a school data model, customer, products, stores in a shop data model. Entities are converted into tables when converting an ERD diagram into database tables. Entities consist of attributes, and attributes are represented by an oval box. Attributes basically tell us description, or it gives us more information about the corresponding entities. Attributes are converted into columns when you are converting your ERD into tables. So entity becomes the table and attributes become the columns. Now there are some common types of attributes. Simple attributes, it is like student first name. Composite attribute, whenever you hear the word composite in terms of relational database, think of something coming together and making a one. Example, composite keys. Composite keys mean more than one keys come together and they form a single key. Similarly, composite attributes means more than one simple attributes come together and they create a new attribute. For example, address. An address consists of house number, zip code, city, state, country. So it's a composite attribute. A single value attribute. These attributes are generally your personal ID numbers like Aadhaar card, SSN, PAN number, which will always stay same for any given customer or any given person. Multi-value attributes are like phone numbers. A person can have more than one phone number. You can have a main phone number and an alternate phone number. Then there are derive attributes. So you can derive a person's age from the date of birth. So date of birth is a simple attribute, but you can derive age from it. And last but not the least, the key attributes. Key attributes are unique, cannot be null, and are associated with entity that helps in identifying the rows uniquely. For example, username. So if you try creating a username in some website, say you want to create a new Gmail account, it will ask you to create your username. And many times you will see a prompt that this username is already taken. So username is a key attribute, it cannot be repeated. Coming to relationships, entity relationship has two types. Entity we already covered. The next component is relationships. And relationships tell us that how different entities interact with each other. It is represented by a diamond box in the ERD diagram. Some examples of relationships are: a student can enroll into different courses. A student can be part of one class only. A class can have many students. A faculty can teach many students. A course can have many students. A customer can place many orders. An order is tagged to only one customer. An order can have many products. A product will belong to a single category. A category can have many products. See, I've given here many examples, and these all examples are very much relevant. So you see student, courses, class, faculty, customer, order, product, all these are entities. And how these entities are related to each other? Like a course can have many students. Course is an entity, students is an entity, and a course means one course mapped to many students. So one to many mapping is there. A student can enroll in many courses. So one to many mapping there also. So if I talk about course and students, I may end up having many to many relationships. Relationships are generally defined using cardinality. Cardinality tells us how rows in one table are related with rows in another table. There are three types of cardinality. One-to-one, like a person can have only one passport, PAN card, Aadhaar card, and that document is also tagged to one person only. It is not possible for a person to have more than one passport. At the same time, it is also not possible that a passport is tagged to more than one person. So there is a one-to-one relationship. Let's talk about next, which is one-to-many. So a customer can place many orders, but an order can have only one customer. So you see here, you go to any online e-commerce platform and you can place multiple number of orders. But each order will be tagged to your customer ID only. It is not possible that order 1 is tagged to you as well as the same order 1 is tagged to some other customer. So there is a one-to-many relationship. The third kind of cardinality is many-to-many. Example can be, a student can enroll in many courses and a course can have many students. So there is a many-to-many relationship between student and course entities. In some time, we'll create an ERD diagram and then these things will become more clear to you. So first, let's quickly go through the theory and we'll do a hands-on also in the later part of the video. Once we have the ERD diagram ready, the next step is to create a third normal form tables for it. So as I said earlier, entities will become tables, attributes will become columns, and relationships will tell us what is a primary key and foreign key relationship between the entities. So in normalization also, we'll talk about first normal form, second normal form, and third normal form. There are more types of normalization, but we'll limit ourselves to first normal form, second normal form, and third normal form as part of this video. The first normal form tells us there should be no repeating groups. It means if there are similar columns or the repeating column values, we have to split it into different rows. And every column value should be atomic. So say you have a full name column, it consists of first name and last name. So you can further break down the full name column into first name and last name. So first normal form says atomic value for each column and there should not be any repeating groups. Moving to second normal form, the table should already be in a first normal form and non-key attributes should be fully functionally dependent on primary or composite key. And the third normal form says the table should already be in second normal form and there should not be any transitive dependency. So when I say transitive dependency, I mean non-key column should not depend on other non-key columns in the table. If that's the case, take out those columns and create a new table. And this will become more clear in the hands-on part we'll do later in the video. Switching to dimensional modeling, it is a database design that consists of dimensions and facts. Granularity is of utmost importance before you design your database. And dimensional modeling is primarily done for OLAP systems. Like normalization, we generally do for OLTP system, where we divide the larger tables into smaller tables, and in order to reduce data redundancy, dimensional modeling is primarily done for OLAP systems. So if you are designing an OLTP system, maybe you'll go for normalization. If you're designing a data warehouse, you will go for dimensional modeling. Now in dimensional modeling, there are two schemas very famous: Star Schema and Snowflake Schema. Star Schema, we identify the dimension and fact tables. There is a centralized fact table surrounded by multiple dimension tables. And granularity of your fact table should be clearly identified before designing your Star Schema. And Snowflake Schema, it is an extension to Star Schema only, where the dimension tables are further split into multiple dimension tables to avoid data redundancy. And it may sound similar to what we do in normalization. So if this part is clear to you, let's go on and do some hands-on. So if you are good with the theory part, let's create our first entity relationship diagram. As I said earlier, the entities are represented in a rectangular boxes and relationship are represented by a diamond box. So we have moved all our entities into rectangular boxes. In this case, I have customer, order, store, products, and category as part of my entities. And then I have established relationship. Customer places order. Orders are tagged to store. Orders have products. Products belong to category. So my very first step while building an entity relationship diagram is to put entities and relationships in place. But there are key components which are missing in this diagram. And those are attributes and cardinality. So adding an attribute is fairly straightforward. Whatever information you want to store about a customer, you can add it. So in this case, for customer, I have customer ID, name, city, email, phone, address. For orders, I have order ID, order date. For store, I have store ID, store city, store zip code. For category, I have category ID, category name, category description. And for product, I have product ID, product name, and product description. So adding attributes is fairly straightforward, and it is a simple task. But the next step of adding relationship and cardinality needs some caution. So let's talk about customer and order. A customer can place multiple orders. So there is 1 to M relationship. An order can be tagged to one customer only. There is many to one relationship. So when I have to generate the cardinality, what I do is I hop from one entity to the second entity and then second entity to the first entity. And I see what is the relationship between the rows that may exist in this entity compared to rows that exist in this entity. So a customer can place multiple orders. One customer can have multiple rows in the order table, but each order ID will be tagged to one customer only. So this way it is one to many, and this way it is one to one, right? So overall relationship becomes one to many relationship. Let's talk about order and store. Multiple orders can go to one store, and one store can handle multiple orders. So this also becomes one-to-many relationship. Let's talk about product and category. A product can belong to one category only, whereas one category can have multiple products in it. So let me give you one example. If it is still not clear, say you have mobile phone category, and that mobile phone category can have Apple iPhone, Samsung, and all other brands of phone tagged to it. So iPhone can be tagged to only one category, which is mobiles. But mobile category can have multiple products like Apple, Samsung, Xiaomi, right? So it's a one-to-many relationship. Now, order and product is a special type of relationship. It's a many-to-many relationship. How come? One order can have multiple products, and one product can be part of multiple orders. So you see here 1 to M from here and 1 to M from here. So overall relationship becomes many to many. I'll repeat. One order can have many products in it, and one product can be part of many orders. So 1 to M, 1 to M, both ways it is 1 to M. So overall relationship becomes many to many. And whenever we have to handle many to many relationships, even the relationship can have some attributes. So in this case, unit price and quantity are the attributes of this relationship. And to handle many to many relationship, we have to introduce a concept of bridge table, which we'll see in the subsequent slide when we will be creating tables from the ERD diagram. If this ERD diagram is not clear to you, pause the video here, spend some time, because in the subsequent slides, I will be creating third normal form table using the exact same ERD. And if you are ready, let's move. The very first step is entity and attributes in the normalization. So what I have done here is all the boxes here, I have converted into the tables. As I said earlier, entities will become tables. So I have customer table, order table, store table, category table, and product table. And if you can recall, I also mentioned the attributes will become the column names. So all the attributes of an entity are mentioned here as column names. The column name, which is highlighted in bold, is the primary key for that particular table. So customer ID, order ID, store ID, category ID, product ID are the primary key for this table. So we are good with entity and attributes. Again, the next step is relationship. Just like we did it in ERD diagrams, we have to do the same thing while designing physical tables. Let's establish the relationship. We said 1 to M relationship between customer and orders. Customer primary key will come as a foreign key here. So whenever there is a 1 to M relationship, there will be a primary key sourced from 1 to the M table. So in this case, 1 to M relationship between customer and order, customer ID, which is a primary key in customer, will become a foreign key here in the order table. Similarly, 1 to M relationship between store and order. So store ID will go as a foreign key here for order table. Let's talk about product and category now. So even in product and category, we have 1 to M relationship. So by this rule, the category ID, which is primary key of category table, will go as a foreign key in product table. And as I mentioned earlier, the order and products have a M to M relationship. So when we convert it into a physical table, we have to introduce a bridge table. And bridge table will source ID from both the participating tables and will use it as a key. So for order product bridge table, order ID and product ID combination will become the primary. And the attributes of that relationship are added in the bridge table. So is this clear? If not, pause the video, go back. If you have any questions, drop a comment. I'll try to answer it. But this is our normalized table. But do you think this is in a third normal form? Not yet. Because if you see here, the non-key columns, which are like zip code and city, those are not dependent on store ID, right? So what we do in this case is we do the normalization. We split the columns into a new table and we source the ID from here. So in this case, we have created a new table, which is address, and the zip code is the primary key here. And this primary key will go to the tables as a foreign key here. And now the table looks in third normal form to me. And if you are designing an OLTP system, you can go ahead, use this third normal form design and create your physical tables. I hope this is clear to you. If this is clear to you, then only proceed to the next step of converting the third normal form tables into a star schema. If not, go back, watch the video again. If you're not clear with it, I'm pretty sure in the next step, it will add more to the complexity. But trust me, it is not complex. You just have to spend some time. The next step is dimensional modeling. And we are going ahead with star schema. So now forget about those things that we have to avoid data redundancy. That's why we use normalization. This is dimensional modeling, star schema, and we are designing it for OLAP purpose, right? So what the first step I'll do is, I see that product and category, both were having a relationship here, right? And these are similar entities and attributes. So what I will do is, I will get rid of category table altogether. And I will bring this information into the product table itself, right? So you can see category name description. I have moved from here to here and got rid of category table. Similarly, I will get rid of this address table as well. So this is gone and all the attributes or address I have pushed into the main dimension table. Also, one thing you will notice is I am changing the naming convention and adding dimension in front of the table so that it gives an impression that yes, we are switching to dimensions and facts. So my customer becomes dimension customer, my store becomes dimension store, and my product becomes dimension product. And I got rid of address and category now. The attributes have been pushed into my corresponding dimension tables itself. Now you can say that there are redundancies, and yes, there are redundancies, will not deny it. But to handle it, what you can do is, if you have to switch your star schema to snowflake schema, and in that case, if you're building a snowflake schema, you could have retained category and address tables as well. In that case, this will become dimension category and this will become dimension address. But we are building a star schema, so it is okay to merge these attributes into the dimension table itself. So this is clear. Now, one thing which is pending is we have dimension tables now, 3 dimension tables now. We need a centralized fact table, and fact table has measures in it. And I see the measures are here, unit price, quantity, right? So this order will become my fact table now. So in the next step, what I will do is I'll create a fact sales order, and granularity for it is customer level, store level, and product level. Whenever at a technical level, right, if you have to explain what is the granularity basically means the level of detail you are storing in your fact table. But technically, if you have to explain, you can say that all the keys which are sourced from the dimension table into the fact table will determine the granularity. So here I have customer ID, store ID, and product ID. 3 keys I'm sourcing from 3 different dimension tables. So granularity for this fact table will become for each customer, for each store, and for each product, what are the measures calculation. That will become the granularity, right? So, and you can see all the bridge table attributes also I bring into my fact table now. And this looks good to me, right? But one very important dimension is missing presently. Can you guess what is that dimension? That dimension is present in almost every dimension model. Every. If you have guessed it, it's good. Else, the answer is dimension date. So date dimension is always a part of your dimensional modeling. So we'll create another dimension here, which is dimension date. It will have its own columns. And date ID is also sourced into fact sales order. So if I am calculating, and my granularity has also changed now. So assuming that date ID corresponds to 1 day, then my granularity becomes, say, sales per customer, per store, per product, per day, right? So each day I can do calculations or calculate measures at customer level, store level, and product level. So this becomes my new granularity. I have introduced a day component as well. And this looks good to me. So this is my final star schema. I'm done with dimensional modeling. If I want to convert it into snowflake schema, I can split these columns, retain the category and address tables, and name it dimension address and dimension category. But if I just want to keep it simple, I want to have a star schema, then this is my star schema. So you see, from ERD diagram, we have come to third normal form, and from third normal form, we have converted to star schema. It's not very complex. You just need some practice. If there is any confusion, any comment, something which is not clear, drop a comment. I'll try to answer your questions. Hope you find this helpful. I really work hard to come up with these videos. If you like it, if you find it useful, do subscribe, like the video, share with your friends. It definitely motivates me. Thank you so much. Have a good day.